So now we're going to take a bit of a detour, and we're going to talk about generative adversarial networks. And these are typically referred to as GANs. So GANs are a special kind of algorithm, and it's very interesting the way that it works. They make two separate neural networks compete against each other. So when we're talking about GANs, we usually have two kinds of network that compete against each other. We have a network called a generator, and the other called a discriminator. And they both have two very specific objectives. The generator has to generate samples that look convincingly real, and the discriminator has to determine whether these generated samples were real or not. So let's try to think of a way to represent this. I like to think of this as a game between a counterfeiter and an art curator. So imagine you're an art curator. Your job is to simply determine whether a piece of art is real or fake. And if you're a counterfeiter, your job is a lot harder. You have to come up with some kind of material that's able to fool the art curator. And if you can fool the art curator, you can make a lot of money. And if you can't fool the art curator, well, then you're not making money as a counterfeiter. So here's a very simple example, right? You have a data set of real paintings. You have your counterfeiter, or your generator, that suggests a painting. And the discriminator here has to say, well, based on the data set of real paintings, is this a real image or not? Is this a fake, or is this a real? By the way, this is a real example. This actually happened. It wasn't a counterfeiter trying to pass this, but it was someone who tried to restore this painting. And unfortunately, this is what came out. So you can imagine that when the curators looked at this, something said, I don't think that this is the original piece, how it was intended to be represented. Now, as you train your generator, it can get better and better. So here we have another example with our generator. We have a piece that might look convincingly real, and if you're not such a good art curator, you might be able to get fooled. Right? So in this case, this is the original painting by Picasso, and this is actually a painting that was done by a 12-year-old. He actually turned out to be a very successful counterfeiter and made lots of money as a counterfeiter. There's a link here. You can go and read up on this guy's story, but I think he made like in the hundreds of millions of dollars by fooling art curators. So mathematically, these can be expressed as what's known as a min-max game. So we have, again, these two networks pitted against each other, and we have a generator trying to minimize an objective function, which we define here, while the discriminator is trying to maximize the subjective function. So simultaneously, the discriminator is trying to fool, the generator is trying to fool the discriminator, and the discriminator is trying to figure out how the generator works. So this is the whole equation sort of behind the original GAN implementations. And here, so I'm defining a few different things. So D of x, this is our discriminator, and G of z, that's our generator. And D of x, you can essentially think of it as a neural network that says, what is the probability that a sample is real? And G of z is a neural network that creates an image and tries to fool D of x. So when we're training these, we want the generator, its goal is to minimize this function. So this is what the generator is trying to minimize, this term right here. And so we want when we're talking about this minimization here, what we're trying to say is we want to maximize the error that D will make on a generated image, G of z. Also, we want the discriminator to maximize the terms in red. So the discriminator wants to get as many images that are real and classify them as real, and as many images that are fake and classify them as fake. So this is where we get this min-max game. They're each trying to generate their own, they're each trying to minimize or maximize their own objective. And in fact, in the original paper, if you look at the algorithm, this is again, the figure taken directly from the paper. So we iteratively go between the two. So we first train the network to maximize by ascending the stochastic gradient descent. So here we're updating the discriminator for a few steps, and then we step over, and for a few steps we try to minimize the objective of the generator. And we go back and forth, and it's this fine game where if the discriminator gets too good too quick, the generator can't learn and can't fool it. And if the generator is too good, then the discriminator doesn't get too good. So it's really this fine balance between the two. And it turns out that we can generate some really interesting stuff. So this is a figure from the original paper on GANs. And so here you see digits that were generated. So these are digits that were never seen before. They were trained on MNIST. And so you can see some examples here of digits that were generated. And here they pick what they found to be the closest digits in the data set. But again, the network was able to learn by never having really seen digits before, but by just trying to fool the discriminator, how to come up with some realistic looking digits. And they did the same thing with images. So here were some real images that they used on a data set, and these were some images of faces that the network came up with. So they're a little bit scary sometimes, like this one is a little bit scary, but this was one of the first, this was the first paper on GANs published by Ian Goodfellow. And in fact, the story goes that this kind of architecture, or these kinds of algorithms were actually figured out at Les Trois Brasseurs, which is a brewery in Montreal. And they were just chatting together and kind of had this idea that, this crazy idea that maybe if you pitted neural networks against each other, it might work. And it turns out that it did, and it blew up, and now there's a whole field in GANs. And if you look at the original paper, they actually they thank Les Trois Brasseurs in the contributions. So yeah, I don't know exactly how much of that story is true, but they definitely thank Les Trois Brasseurs in their paper. So why are we talking about this? Well, once the GAN paper came out, people thought, let's apply convolutional neural networks to GANs, and let's see what we can do with these. And it turns out that, first of all, they used transposed convolutions for doing these upsampling. So we spoke a little bit about the transposed convolution, and this is where it's really useful. Up until now, for the classification, we're only reducing our volumes, but now we're using this concept of transposed convolution to upsample our images as well. So we can get our networks to learn based on some kind of noisy signal as an input. We upsample and we upsample until we get some realistic image. And in this paper, in the DC GAN paper, which I recommend you go read, the link is over there, they do some very interesting face arithmetic. So what they do is they take a smiling woman, they subtract the representation of a neutral woman, and they add the representation of a neutral man, and what they get is a smiling man. Right? So they're able to show that by using the features that the networks learn, they're able to do this arithmetic in this GAN space. And fast forward a few years later, we then have some really, really interesting research, a lot more work being done into generating some very realistic looking faces. So this is some work that was published by NVIDIA recently. So now let's play a game. Let's try to figure out which image was generated by a network and which image is real. Okay, so take some time to look at these images. And let's vote by just raising our hands. So who thinks that this is the real person? Okay, we have a few hands. And who thinks that this is the real person? Okay, all right. So it seems like most of you think that this is the real person. This is a generated person. In fact, it turns out they're both generated. It's crazy how much detail goes into these images, and it really can fool most people. If you look closely, like if you look at the ear over here, there's a little bit of some artifact. I don't blame you. It might be hard to see based on the projector. Even here, like you can see a few artifacts. But again, all that to say that if you are able to put these networks together in an intelligent way, they can then learn these really interesting representations. We can also do something called style transfer. So in this paper, what they do is they take a specific image and they take another source image and try to fuse the two. So if you combine these two people, what would they look like? So for example, take this person over here, take this child over here, and if you had to represent this person as the mix of this person and this child, this is what your network generates. Right? So it's these really interesting ideas, and you can imagine all sorts of work that can be done, and they're pretty convincing. Again, look at all these representation of children here. So you take this person as the source, and you say, well, represent this as what's being shown here as a child. Now, of course, in the age of deep fakes, there's a lot of worries about fake news. I like to think about the more positive applications. So here we have someone who wasn't really satisfied with how the new Lion King looked and decided to do style transfer and take the realistic Lion King and project back to the old Lion King. So again, a really kind of neat use of style transfer here, where we can get these cartoon representations based on the real images. All right, following, so a bit more work on GANs. Something really interesting is the concept of cycle GAN. So many of you probably have seen that Face app that went viral a few weeks ago, where you take someone's image and you convert them into an older looking person. So obviously I played with it. So you take your image, you put it in. So I took a selfie and then it generated me as an old man, right? And this, well, I'm not entirely sure how Face app works specifically, but it's probably something close to what cycle GAN does. So in the concept of cycle GAN, they introduced the concept of cycle consistency loss. And this is a really, really interesting idea. The way that it works is that you want to train your network to be cyclical. So if you take an input, so say myself, and you have some kind of generator that generates aging, you also want to train another network that's a de-aging generator. And the idea is that when you pass the image to the aging generator, to the de-aging generator, it should then be able to fool another discriminator whose job is to determine whether this is a young person or not. So you train these networks in this cyclical fashion, and you can then go and map realistically from one domain to the next without necessarily having images that were explicitly trained to be directly mapped. And this is the loss that's defined in their paper. I'm not going to go into it too much into detail, but again, their contribution here is this cyclical loss that they added to the GAN loss that we saw before, where the reconstruction of the image has to be as close as possible to the original image after going through all of these steps. So we can get some really interesting results with this. So for example, here, we can map a horse to a zebra in a very realistic way. I don't know why you would want to do this, but you can. And again, this is some really amazing work. I recommend going to read the original Cycle GAN paper. It's really well written. There's also all the code available to generate these examples and generate your own examples as well. And some other examples that you could do with this is take, for example, a painting of Monet and transfer it into a realistic-looking image. Conversely, you could take a realistic-looking image and say, convert this into the style of Monet or Van Gogh. And you can do some really, really cool, you can have some really cool applications with this. Another thing that you can do is colorize images. So if you have some old black and white images, you can then figure out techniques to colorize them for them to be as realistic as possible. Okay, a really cool one as well, GAN field. So someone thought it was a good idea to use GANs to generate Garfield images. So what he did is he just collected all of the Garfield comics that he could find, generated this ginormous data set, and just got the generator to generate new Garfield panels. And it's kind of trippy, but realistic, right? This kind of looks like Garfield, other than the text, and there's reasons why the text didn't come out very well. The person details it pretty much in very good detail in their blog post. I recommend you read it. It kind of gives insight as well into the whole pipeline that goes into collecting your own data set and what can go wrong. But again, we really see Garfield's face being reconstructed. Garfield looks to be going through different dimensions, which I think is kind of interesting.